Let me introduce myself. I am Dr. C.J. Ramankutti, retired professor of chemistry from Union Christian College, Alway, in Kerala. I love chemistry students, and of course chemicals. And today, I wish to give an introduction to molecular symmetry. The word symmetry means regularity in shape. As chemists, we are interested in the shapes of molecules and describing their regularities. Hence the title Molecular Symmetry. Evidently, a definite prerequisite for studying this topic is a knowledge of shapes of molecules. The basic method of testing the shapes of molecules is by doing some movements of the molecule and looking for whether the molecule returns to the same appearance, indistinguishable from its original look. To do this testing, we make use of symmetry elements and symmetry operations. The symmetry elements are fivefold. Let me list them here on the board. Axis of symmetry of order n, denoted by a symbol Cn. Secondly, plane of symmetry, symbolized as sigma. Thirdly, center of symmetry, denoted by I. Fourthly, improper axis of symmetry, denoted by Sn. And finally, identity, symbolized by E. What is listed here are called elements of symmetry. As these names indicate, elements of symmetry are geometric entities, real or imaginary, pertaining to the molecule, like an axis or a line, a plane or a central point, again an axis, or the whole molecule itself, about which we carry out some movements. These movements are called symmetry operations. So let me list as a second column the operations corresponding to axis. The operation is rotation. Corresponding to plane, it is reflection. So center of symmetry, inversion. Improper it is rotation, reflection. And finally, for identity element, the operation is just the act of doing nothing. Leave the molecule alone. Act of doing nothing. So using these symmetry elements and various movements about this, we check whether the molecular shape has some regularity or other. Each of these can be elaborated in detail. First, let us concentrate on axis of symmetry so that I will rub off all the others. As mentioned earlier, axis or line of symmetry is a real or imaginary line passing through the molecule. It has to pass through the molecule such that if you carry out a rotation about this line by an angle of 360 by n degree, the molecule returns to its original appearance, indistinguishable from its appearance at the beginning. We have axes of symmetry of various orders, starting from 1 to infinity. An axis of symmetry of order 1 is unimportant or insignificant because any object, when rotated by 360 divided by 1 or one full rotation, as if the object has somersaulted, whether it has symmetry or no symmetry, it will definitely return to its original look. It will come back to its look as if nobody has tampered with it, nobody has disturbed it. So if you write C1, it is equivalent to doing nothing on the molecule because the molecule returns to its original appearance as if no movement has been carried out about it. And because we have a notation for the act of doing nothing, leaving it alone operation done on the whole molecule, we may write that C1 is the same as the so-called identity, as if nothing has been done on the molecule. What is more important are axes of n value greater than 1. Think of a molecule like ammonia. We all know that ammonia is a pyramidal molecule. I have a ball and a stick model of ammonia molecule here. I am holding it by this line. If I keep it on the board in this manner, you notice that the 3 hydrogens are touching the board and the pyramidal nitrogen atom is projected above the plane of the board. We can draw a picture of this, a projection of this on the board as H, N, H, H. The model overlaps with my projection on the board. And if I rotate this molecule about this line in this manner, at every 120-degree rotation, I am getting the same appearance, This angle is 120 degree in this projection. Suppose I rotate it in this direction. (120 degree) happens to be 360 divided by 3. So I can symbolize this axis by C3, and for the number obtained by 360 divided by the angle over which it is rotated. It returns the same appearance. Now I am not supposed to move this molecule from this spatial position to this position while checking symmetry. This has to remain here itself. This is the correct way of doing it. But the new appearance on 120-degree rotation will be overlapping with this to avoid the overlapped look of the new appearance and old appearance. For our convenience, I wrote it a little bit slightly away to the right side. Now, in order to know whether this appearance and this appearance are exactly alike, we may, for our sake, number these hydrogen atoms as 1, 2, and 3. Actually, there are no numbers. It is only for distinguishing among the hydrogen atoms we have labeled it as 1, 2, 3. And by this rotation, I have done the rotation in the anti-clockwise direction. This 1 has come to this position, 2 goes up, and the 3 comes here. Let me label appearance at the start as 1 and appearance after 120-degree rotation as 2. Without the labels and without imagining that it is moved to the right side, appearance 2 and appearance 1 are indistinguishable. But because I have put labels, you can say that this appearance 2 is not exactly like appearance 1 because the atoms have different identities. This type of look, which is without a number, is indistinguishable from the original look, may be called an equivalent appearance rather than an identical appearance. For testing symmetry, it is enough that after the movement is done, the molecule returns to an equivalent appearance. And you can repeat these movements as many times as you wish. For example, after reaching the appearance 2, I can do one more 120-degree rotation, of course in the anti-clockwise direction, and let us see how the molecular appearance is to be written now. The 1 will go up, 2 will be here, and 3 will come here. Let me call it as 3. Because of the labels, 1, 2, and 3 look different. In one, hydrogen 1 is to the left, here hydrogen 3 is to the left, here hydrogen 2 is to the left. That distinguishes each appearance. But the distinguishing label was put by us. There is no such a label in reality. But if you do one more 120-degree rotation, let us see how it looks. This 3 will come to the top and 1 will be here and 2 will be here. And let me call it as 4. Now compare 1 and 4. Between 1 and 4, the appearance, even with the labels, are the same. So if I take this 4 and overlap with this 1, there is no way to know how 4 differs from 1. Even with the labels, they look alike. This type of two appearance of the molecule which are indistinguishable even with the labels. You may call it as an identical appearance. It is as if you have not tampered with, you have not disturbed the appearance 1, because appearance 1 and 4 are the same. This type of look is as if 1 is not disturbed at all. And that type of never disturbed at all is indicated by its notation identity. And how do you get identity? After doing the 120-degree rotation successively, first, second and third, 3 times. I will symbolize it as C3, one more C3, one more C3, or C3, 3 or C3 cube. It is the same as identity. The repetition of 120-degree rotation can be repeated as many times as you wish. But let us see whether you are getting any new appearances other than 1, 2, 3 or 4. What will be the look of molecular shape if after C3, you do one more C3 so that it is denoted as C3, 4. It is very clear that if one more rotation is done on this 4, it will go back to appearance 2. As if the original molecule is simply rotated by 120 degree. So I will write that C3, 4 gives the same, even with the labels 1, 2, 3, etc. put on hydrogen, as appearance 2. So we can write an equation C3, 4 is the same as C3, 1 or simply C3. You don't have to write a 1 here. And what about C3, 5? It will give appearance 3, as if just C3 followed by C3 are done. 2 C3s, one after another, can be symbolized as C3, 2 or C3 squared. What about C3, 6? It is as if the original appearance is done, just one 360 rotation, C3, 3, and again a 360 rotation, and final look is as if nobody has disturbed it. The appearance is indistinguishable, even with the labels written on the hydrogen 1, 2 and 3. Or C3, 6 is the same as identity. And the pattern can be repeated. So if how many times you may do the C3 rotation, the ultimate results are either C3 or C3 squared or identity. This identity, the act of doing nothing, although it is extremely trivial, is an extremely important operation to be included in discussing theory, and after the theory of symmetry, in discussing group theory. Any molecule will have an identity operation. So mentioning this identity repeatedly is unimportant. Identity is always there. Even the most unsymmetrical molecule has identity. So apart leaving this identity away, the presence of a threefold axis of symmetry, so many times you may repeat that, is bringing the molecule back to an appearance as if just a C3 is done or a C3 squared is done. Nothing else. Keeping away the identity. It is as if you just do a 120 rotation or 2 into 120 or 240 degree rotation. We say that the presence of a threefold axis of symmetry generates simply two operations which are C3 and C3 squared. These two cannot be represented in any other simpler way than by these notations themselves. Such operations which cannot be expressed in any other simpler way than by itself in terms of other operations are called distinct operations. Our conclusion is a threefold axis of symmetry always is associated with two distinct operations, C3 and C3 squared. Let us explore the other axes of various orders. The simplest, leaving aside the C1, it is C2. The molecule water, a V-shaped molecule. If I put 1 and 2 as labels, and if imagine a line like this, and if I rotate it in the anti-clockwise direction, 180 rotation is denoted by C2 because 2 is 360 divided by 180. This gives the same appearance. Of course, the two hydrogen atoms have exchanged their places. The 2 has come here and 1 is here. So appearance 1 and appearance 2 with the labels are distinguishable, but without labels they are indistinguishable. They are equivalent appearances. That is sufficient for the existence of symmetry. But if I do one more C2, I am getting the appearance where 1 comes here, 2 comes here, and we can see that 3 and 1 are the same. 3 and 1 are the same. So doing 180 degree rotation successively 2 times, you are getting a result as if you have not done anything on the molecule, as if leaving it alone. No movement done on the molecule is reached. So we will call it as identity. So C3, 3 was identity, C2, 2 was identity. And if this discussion continues, it is a very clear fact that CNN always will be identity. It is important to remember to create such equations. How two operations are mutually equal. In going further in group theory, these types of equations become very important. CNN becomes identity. Let us go through molecular examples having C4, C5, C6, etc. Before that, an important point is coming to my mind. Writing again the ammonia molecule, and this being the axis we call C3 axis. We illustrated its rotation by 120 degree in the anti-clockwise direction. So a person can ask, what is the problem if the rotation is done in the clockwise direction? in the anti-clockwise direction, when 120-degree rotation is done, the picture was 1, 2, 3, and one more rotation in the anti-clockwise, the picture was 1, 2, 3, and I wrote these appearances as first one C3 it is 2, and one more C3 it is 3. If I do the rotation of this in the clockwise direction, in this direction, clockwise direction, just by 120 degree. Clockwise direction is denoted as positive direction. So I will write positive 1. You can see that 1 comes at top, 3 comes here and 2 comes here, exactly like you got 3. If clockwise is the positive direction, anti-clockwise is the negative direction. So how did you get 3 from 1? By anti-clockwise rotation. Rotating it by 120 degree once, then one more 120 degree once. 2 such rotations in the anti-clockwise direction. If clockwise direction is plus, anti-clockwise is minus. And 2 such rotations, I'll put it as C3 to the or minus 2. And C3 positive direction 1 is giving the same result as C3 squared in the anti-clockwise direction 2 times. So we can write an equation like this. But if you study symmetry further, denoting clockwise direction as positive and anti-clockwise negative, you are likely to get more confused in the study of this subject. So, as my own teacher, Dr. K.L. Sebastian of Indian Institute of Science, Bangalore, has suggested, it is better we stick to always one direction of rotation. And we will fix it as anti-clockwise. If we fix the direction of rotation as anti-clockwise, forget about denoting the plus and minus sign. Always do it anti-clockwise. There will not be so-called accidents in grasping the results. It is better to avoid plus and minus sign. But in some textbooks you may see these. That is why I mentioned it. So from hence onwards we will not put any plus or minus. We assume and accept that any rotation done on the molecule about an axis is always anti-clockwise. Okay, so that matter is settled. I'm rubbing it off. Think of examples with higher axis of symmetry. A C4 axis is possessed by this famous complex tetrachloridoplatinate 2. It's a square planar complex. If I label the chlorines as 1, 2, 3 and 4, 90 degree rotation creates the same appearance. Of course, the labeled atoms get changed in their positions. 1, 2, 3, 4. One more C4 brings it as anti-clockwise. Chlorine 1 here, chlorine 2 here, chlorine 3 here, chlorine 4 here. One more C4, C4 1, C4 second, C4 3. One here, 2 here, 3 here, 4 here. Let us do one more. I will better write it like this, C4. So that anti-clockwise, 4 comes here, this is the direction, 4 comes here, 1 comes here, 2 goes here, 3 comes to top. So 1 C4, second C4, third C4, fourth C4. Successively, C4, 4 brings back the molecule to its original appearance, including the labels on the chlorine atoms, as if you have not disturbed it. So we got the result, identity. Now what are the distinct operations generated out of this? C4 is a distinct operation, no doubt. There is no simpler way of expressing it. But what about C4 squared? C4 squared, if this is appearance 1, this is appearance 2, this is appearance 3, and this is appearance 4. C4 squared changes the molecule from appearance 1 to 3. 1 to 3. Now suppose a person, by overlooking to stop the rotation at 90 degree, decides to rotate the molecule about that axis in a single stretch by 180 degree. He will end up from appearance 1 to appearance 3 in a single stretch of rotation by 180 degree. And he will claim that that particular element of symmetry is a C2 axis. And we cannot say that what he said was wrong. He said was right. So this C4 squared is giving the same result as if you have done a C2 rotation about a line which is now better described as a C2 axis. Of course, it is coincident with our C4 axis. So when C4 squared and C2 are both turning the appearance 1 to appearance 3 equally, that operation is better described in a simpler term, C2 rather than C4 squared. And if you write C2 for that operation, the C4 squared is something not needed to be mentioned, or it loses its distinctness. So we will include C2 and forget about C4 squared. So first C4 is there, C4-2 is not a distinct operation because it is being expressed in a simpler way in terms of another operation, C2. 180 degree rotation is the same as 90 degree rotation successively 2 times. And writing C2 is a simpler way rather than C4-2. So we will accept C2 and forget about C4 squared. But what about C4-3? 90 into 3. 270 degree. There is no other simpler way of expressing it. So C4-3 is a distinct operation, but C4-4, 90 degree into 4, that is whole 360 degree rotation, as if you bring back the molecule to its original look, as if nothing is done on the molecule, as if the molecule is left alone without any disturbance, and for which we have used the notation identity. So C4-4 being equal to identity, and identity is present for any molecule. It is always included in our list of operations, and this becomes not distinct. Analyze the situation for molecules with higher and higher order access. Everybody should be familiar with C5H5 minus. Cyclopentadienyl anion. Cyclopentadienyl anion. It is a non-benzenoid aromatic stable system, and this will be a C5 axis. Every 72 degree will bring it to the same appearance. So there is C5 as a distinct operation. C5 squared will be another distinct operation. Likewise, you have to continue. When you reach C5,5, it will be identity. A more popular example is benzene, which has got a C6 axis. Every 60 degree will bring it to the same appearance. So there is C6. We can repeat it. C6 squared, C6,3, C6,4, C6,5, C6,6. But among these, which are the distinct operations? C6 cannot be expressed in any other similar way. So it is a distinct operation. But C6 squared, 60 into 2, 120 degree, can be done in a single stretch rotation of 120 degree, and the person can call that axis as a C3 axis. And what he said is correct. So instead of writing a C6 squared, you can call it a C3 axis, which is a simpler way of expressing that operation instead of C6 squared. And C6,3, 60 into 3, 180 degree. That same line, coincident with our original C6, you may interpret it as a C2 axis, as if 180 degree rotation is bringing the same appearance. And once it is C2, you don't have to say C6,3. Their distinctness are lost. C6,4, it is 60 into 4, 240 degree. 60 degree 4 times successively. Another person can say 120 degrees successively 2 times. That will be making it C3,2. And C3,2 is the simplest style of expressing C4,6. So this is included and this one is not distinct. C6,5, it is distinct. C6,6, it is identity. So you notice that the presence of a C6 axis generates in the molecule only 2 distinct operations in terms of C6, which is C6 and C6,5. Others are denoted in simple terms by simpler numbers like 2, 3, etc. rather than 6. It is important to make sure the distinct operations present in a molecule, because it is this list of distinct operations make the mathematical group out of the symmetry operations. It is the identifying the group in terms of symmetry operations is a basic requirement in developing group theory. There are examples for 7-fold acts of symmetry. In the case of C5, what was the angle I said? 360 divided by 5, it is 1. (72°), correct? 72°. But C7, the angle will be 360 degree divided by 7. Seven into 5, 10, 10 by 7, point 3 by 7. So much degrees. This organic molecule C7H7 plus tropylium cation. 1, 2, 3, 4, 5, 6, 7 has a 7-fold axis of symmetry. There is a complex a sandwich compound of formula U C8H8 twice. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Cyclooctatetraenol dianion. Cyclooctatetraenol dianion. Sandwiched between these there is uranium. Uranium is the plus 4 state, and these two are negatively charged. It is a non-Benzene aromatic system, obeys Hooker's rule, and this, it is a either eclipsed or staggered, it will have a C8 axis. Coming to linear molecules like HCl or oxygen, atoms are spherical in shape. This will be a C infinity axis. All linear molecules have got a line passing through the molecular axis as a C infinity, because any iota degree rotation will bring the molecule to its own appearance. So in the molecular world, we have symmetries of axis from C1 to C infinity. It is possible that a molecule can have, in addition to an axis of high order as C6, other axes of similar orders. For example, here is an axis, here is an axis, here is an axis. In the plane of the molecule, all these are C2 axes. Not only that, a line bisecting the opposite sides of benzene ring, these three are also C2 axes. So there is C2, C2 dash, C2 2 dash, C2 3 dash, C2 4 dash, C2 5 dash, and C2 6 dash. 6 C2 axes. These are the other ends of these axes. In addition to C6 axis, it has also many C2 axes. Then we say that the axis of highest order as the principal axis, and others may be called the subsidiary axis. Benzene has C6 as the principal axis and 6 two-fold axes of symmetry, which is not the principal one, it may be subsidiary. In a situation like ethylene, it's a planar molecule. Here is a C2 axis, here is a C2 axis, and a line perpendicular to the plane of the molecule passing through the middle of the carbon-carbon double bond is a third C2 axis. So all the three are C2 axes. Then what will you call as the principal axis? If some uniqueness is chosen for calling it as a principal axis, for example, this one passes through carbon atoms, whereas this line and this line are only passing through or bisecting the carbon-carbon double bond. So there is uniqueness about a line passing through the carbon atoms. It is chosen as principal axis. Sufficient points have been covered about axes of symmetry. In our next class, we shall worry about discussing plane of symmetry. Thank you for your patient listening. Thank you.